Simulation. So, yeah. The last thing in circular motion is what causes circular motion to occur in heavenly bodies. And by heavenly bodies, I don't mean your boyfriend or your girlfriend. I mean planets, moons, stars, and the like. Doesn't work that way. Okay, so universal gravitation is actually a pretty slick idea, and it is unique to my knowledge of, it is something that as a law has two different theories that explain it. Ordinarily, we remind ourselves that a law describes what will happen, and a theory describes why something will happen. So a law says this will happen, a theory says this is why it will happen, and with gravity, we have two theories that both work. Ordinarily, that would not happen. You wouldn't have two theories that both work. They would conflict in some way. Not gravity. We actually have two theories that occur simultaneously with gravity. So our discussion about gravity entails 5 individuals. These 5. Anyone have an idea who that is? Aristotle. Yeah, Aristotle. He was a philosopher, not a scientist. So he thought about stuff. And normally, a lot of our discussions of science, most of science, start with Aristotle. He kind of got the ball rolling. Almost everything he said was wrong, but at least he got the ball rolling. Anyone have any idea who this guy was? Galileo, yeah. So Galileo, one of our first scientists who decided let's try something, and they did an experiment. And then the most important individual being who? Newton. In fact, the science that you learn in this class is Newtonian physics. Age. And then you probably don't know who this guy is. Anyone know who this guy is? George Washington. No, it's. I can see George Washington.
Like, no, that's not right.
Not George Washington. George Washington was instrumental in physics. No, this is a guy named Cavendish. A guy named Cavendish. Yeah, and you don't know him because he didn't have a story. He needed a story, like Galileo and Newton had a story. And then of course this guy, Grandpa. Yeah. Isaac Newton or Albert Einstein.
Yes. We have
That looks like Grandma. Okay, so Aristotle, Galileo, Newton, Cavendish, and Einstein. So here's the beginning of our conversation about 3,000 years ago. Galileo wasn't on the scene. There was no scientist. There were just philosophers, and philosophy means love of knowledge. A philosopher is a love, philo, of knowledge, like the city of brotherly love. The most ironic name for a city ever. So there was just philosophers, and Aristotle and his buddies would hang around and they'd talk about things. And Aristotle believed in this idea called natural motion, where things that were heavier would naturally fall down. And if something had 10 times the mass, it would naturally, you don't need to write this down. You need to write down the formulas, but you don't need to write down the stories, unless you're interested in this stuff. I was interested. I like science trivia. I score a lot of points in Jeopardy. But it's the formulas you need to write down. So the cool thing about Aristotle is he got the ball rolling. Most of the stuff was wrong, including this idea about natural motion, where if you had 10 times the mass, something would have 10 times the tendency to fall. So it would fall 10 times as fast. Made sense. Because if you're dropping something on your foot, it appears that heavy objects and light objects fall, and you can't see if they fall faster or slower because we didn't have good clocks then. But we did know that a heavy object fell on your foot and it hurt more than a light object. So it made sense that a heavier object would fall faster. And then we all know the story. It's probably apocryphal. It's probably a parable. Whether it happened or not, we don't really know. But the idea was Galileo took a big rock and a small rock, and he put 2 students at the bottom of the tower, and he dropped the rocks. And to hear, ow, ow, or to hear, ow, 1 ow, right? You heard 1 ow. So that's the idea. Whether it happened or not, again, it's apocryphal. It's a parable. Maybe it happened, maybe it didn't. But the idea was Galileo, one of our first scientists, proved that by doing experimentation, all objects fall at the same rate because of gravity. Okay? Make sense? Questions? this guy named Johannes Kepler, which for some reason is kept out of a lot of science textbooks. I don't know why. He looked at a bunch of data, astronomical data. We have our telescope, yay, Galileo, and a few others. And we have our telescopes. We're looking at astronomical data. We're looking at planets and stars and comets and such. And Kepler realized that objects, heavenly objects, move in ellipses. They move in elliptical orbits. And then doing a little bit of math, Newton came along and he said, you know what? Based on that data, we can realize that the force of attraction is related to the speed and how far they are away from the center of their orbit, called the foci. And using that information, he found that the force of attraction between the sun and the planets going around the sun, the Earth and the moon going around the Earth, was varied inversely with the square of distance. And he had already done his calculus, and he's like, okay, calculus is cool. So we have F equals ma, and A, you remember, equals what over what? Yeah, v squared over r. So putting this together, we were like, okay, then that means VFC equals m v squared over r, which is great. Here given a d, here given an r, that, you know, basically force is varies inversely with the square of distance, which is kind of neat. And there's our centrifugal force, mass, velocity, and so on. That was great. And using this information, yes?
What is that sort of, I don't know what to describe it as, but the F?
This is varies with.
Okay.
Meaning it's not an equal sign because something's missing. It varies with. So force varies with 1 over the square of distance. This is called the inverse square law, by the way, and it comes up a lot. This idea of the inverse square law. Things fall off with the square of distance. Light falls off the square of distance, sound and so on falls off the square of distance. Energy falls off the square of distance. Okay, this is kind of neat, but we didn't really have a formula yet. So he put stuff together, he realized that mass was an issue. The more mass you have, the greater gravitational force you have. And the idea was, again, the apocryphal story is, Isaac Newton's sitting under an apple tree, he's watching the apples fall, and he thought, huh, what's pulling the apples down? The Earth. Well, if everything else has force pairs, wouldn't it make sense that the apples are pulling up on the Earth? And they would. So his idea that they would, as he explained it. So the masses of the objects played a part in the force between them. And he came up with this formula, which we call Newton's law of universal gravity, or gravitation. It is F. Now we've gotten rid of the varies with, and we actually have numbers in here, variables in here. F equals G, m1, m2 for the masses of the objects, and the square of the distances between their centers. And F is just a gravitational constant. It's just some number. There are lots of constants that make math work, but right now it's just a constant. So what this says is the mass of the two objects determine the force between them, and the square of the distances between them determines the force between them. Kind of like this. Leaf is attracted to Michael because Leaf has mass and Michael has mass. Okay? So there's a force of attraction between them. But Braden is a lot strongly more attracted to Michael because he is closer. Although, and some other factors too. So, although Leaf and Braden both have mass, since Braden is twice as close, he has 4 times the attraction for Michael than Leaf does. Does that make sense? So, when you're cuddling up with your BFF or your boyfriend or your girlfriend, and you're like, if we got twice as close, there'd be 4 times the attraction.
I'll keep that.
And then she would say, yeah, that's a great idea. Let's get twice as close, it'll be 4 times the attraction. If we got 3 times as close, it'll be 9 times the attraction. So that's Newton's law of universal gravity. So when you need to ask somebody out to Sadie's or to prom, you can use science. You can say, hey, I noticed you have mass. I also have mass. Newton's laws tell us, since we have mass, there's an attraction between us.
Oh my God.
She falls for it every time. Okay.
I'm going to keep this in mind.
Yes. Keep that, write that down. Watch the YouTube. As long as you have mass, and you're like, she's like, great, I'm going to eat a pint of ice cream so I have more mass. There'll be more attraction between us. Okay, so that's great, but we didn't have really good numbers. We didn't have really good numbers, and that's where this crazy guy Cavendish comes along. So Newton had since proved, and it was pretty well accepted, that when you have mass, mass attracts mass. The Earth has mass, the Sun has mass, there's an attraction between the Earth and the Sun. The Moon has mass, the Earth has mass, there's an attraction between the Moon and the Earth. By the way, the Earth does not move in a circle around the Sun. It wobbles. Because it is not the Sun that's attracting the Earth, it's the Sun that's attracting the Earth-Moon system. So the Moon is going around the Earth, and the Sun is attracting that system of two masses. Their center of mass of the Moon and the Earth is not the center of the Earth. It's a little bit towards the Moon. But anyway, so this is where Cavendish comes along. Cavendish gets this great idea to get a huge mass of lead. He gets a huge lead ball. Then he gets another huge lead ball, like 1,000 pounds of lead. Actually, probably several thousand pounds of lead, several thousand pounds of lead. And then, between those two, he puts a bar. And it's like, kind of like what you're making your torque bar, or your torque mobiles. It's a bar with hanging from a fulcrum, and then he puts things on the other side. So he hangs this two-arm mobile in between the two pieces of lead. And on those ends of the bar, he put more metal spheres. Not as big as the lead spheres, but still pretty good size. And then he lets it go. What did the bar do? So you have a huge mass, huge lead mass on the floor. Over here, another huge mass on the floor. So massive ball, massive ball. In between the two balls, you put a swing that was pivoted in the middle with metal balls on either end. And you released it. And what happened? When he released it, it moved. It pivoted that way. It turned. So in other words, the big massive balls were attracted to the little massive balls, causing the pivot, or causing the bar to move. That's called a Cavendish balance. Then Cavendish said, okay, let's go back to my first year physics course. Based on constant acceleration, distance apart, how long they took, d equals 1/2 at squared, there's acceleration. And if I have acceleration, I can plug it back into force, and I can find the force of attraction. And he did. And he solved for g. Kind of like what you're going to be about to be doing in your simulation. He took two masses, he found the gravitational force between them, and he solved for g, and we call this the Cavendish constant. Or if you're lazy, Newton's constant of gravity. But it's Cavendish who proved it. It's 6.67 times 10 to the negative 11. If anybody wants to get me a few thousand pounds of lead, we can recreate the experiment.
I'll get it done.
Yeah. Daniel's on the case.
Do you care how we acquire?
Oh, no.
Okay, then I'm sorry.
Let's see, if you go to the range, you take out all those bullets. One bullet's about 30 grams. You're only going to need about 3 billion bullets. Yeah, no problem.
I was just going to find another way to do it. I can do that too.
Okay, so that's Cavendish constant. And now we have everything we need to find the force of attraction between two objects. Pretty cool. Okay, does this idea make sense? Okay, and this was great for hundreds of years. And then, as he often does, Einstein came and messed it all up. Because Einstein observed, and others observed, but Einstein observed that if you look at starlight, as it passes behind planets like Jupiter, disappears too soon and shows up too soon. it isn't where it should be. Let me show you what I mean. So he said, okay, I'm right here, and I'm looking at a star. If there's nothing in the way, the star is right there. However, if there's a planet in the way, I shouldn't be able to see the star, but I can. The planet should be in the way, but I can still see it. What was happening was the light traveling from the star was bending towards the planet and then encountering my eye. This was a big deal. We could do the geometry and say, okay, based on where Jupiter is, I should not be able to see that star, but I can see it because light was bending towards Jupiter. What did Jupiter have? Yeah, a lot of mass. What does starlight not have? Mass, and that was a problem. So that was a problem because Newton's laws required that the two objects that have a gravitational attraction to each other have mass. Starlight doesn't have mass. Yet it was proved very, very easily that that source of mass was bending starlight. So what did he come up with? What did Einstein come up with? Anyone know? Einstein said, mass does attract mass, but what happens is in a dimension far beyond our own, mass curves space. We exist in 3 dimensions, x, y, and z. And Einstein proposed that masses in those 3 dimensions curve space in an unknown dimension we can't see. Kind of like that. So as far as the light beam was concerned, it's still moving in a straight line. But as it approaches Jupiter, it bends towards Jupiter and then keeps going in a straight line. But as far as it's concerned, it's always been going in a straight line. Kind of like, imagine you took a really tight trampoline and you flipped a marble across it. Where's it going to go? Yeah, straight. But if you put a bowling ball in the middle of the trampoline and then flip the marble, what's the marble going to do? It's going to bend in the direction of the bowling ball. And that's what happens. Objects in space that have mass create gravity wells that bend space in an unknown dimension. Kind of wild, huh? So right now, you are all creating tiny gravity wells in some unknown, unseen dimension, each of you. And the reason that Braden has a greater attraction than Leaf for Michael is that Braden is closer to Michael's gravity well. So he's deeper in the gravity well. Does that idea make sense? I don't recommend asking your date out by saying, hey, I notice you make a big gravity well. You can really curve space. But that's how it works. So again, this is what's crazy about gravity. We have one law of gravity, but we have 2 theories that both work. 2 theories of gravity that both work. Both the Newtonian system and the Einsteinian system both work. So we accept them both. Okay. Here's a fun graphic from XKCD, and it shows a visual representation of the gravity wells. So there's Mercury's gravity well. There's Venus, Earth, Mars, Jupiter, your mom, Saturn. Your mom is so steep, it's just nothing can escape. Your mom's gravity well is extensive. Everybody's attracted to your mom. Anyone that has seen his mom, that's a gravity well right there.
I wonder where the line is and where we crossed it.
Oh, we crossed it a long time ago.
Oh my
Okay.
God,
There is one thing that will never be tested of you in this course, but it is really cool, and that is another aspect of Einstein's relativity. Gravity has another effect. Gravity is goofy. You might have been hearing about the Higgs boson. We want to find the Higgs boson or the God particle, because gravity is very, very elusive. But one of the things that gravity does is it dilates time. Do you know what dilation means? Stretching. Dilation is stretching. So gravity stretches time, and this has actually been proven. When you encounter more gravity, you slow down. They took 2 atomic clocks that were perfect, not to the second, to the millionths of a second. One, they put in a cavern under a mountain. The other one, they climbed up to the top of the mountain and put it right above the other one, perfectly in line, like right above it. They came back a couple years. The one above it, encountering less gravity, was faster. The one at the bottom, encountering more gravity, was slower. You actually slow down when you increase your gravity, which is why fat people can't run very fast. Time for them is a lot slower. What? Now we're offending fat people? Okay.
We're on the roll today.
But the practical aspect of this is, if you were to fly a spaceship into a black hole, as your gravity got higher and higher and higher, time for you would slow down and slow down and slow down. Anyone seen the movie Interstellar?
Yes.
There you go. Okay.
That movie freaked my head out.
Yeah, it's a freaky movie. The math is a little dubious. Yeah, because the speed you have to get to before gravity changes appreciably is enormous, and that kind of speed would cause a lot of other relativistic effects, like tearing you apart.
Oh,
I
that's
couldn't
convenient.
wrap my head around time being like speed and
I don't know.
Fluid.
yeah, like
I
how
saw
they were
space.
like talking about how it was like gravity kind of where it was like it hurt my head. I was like,
Because
Okay, Jared.
the idea in that movie, if I remember, I've only seen it once. If I remember correctly, is there is time can basically act as a bridge between points in space.
Yeah.
It can go forward and backward, and those unseen dimensions that we don't entirely know about, we like to play with that idea that you can go back and forth between places using time and gravity. Wormholes have been around since the 60s. The idea is if you have a huge source of gravity, it'll warp time and space to connect 2 points together. So instead of space, imagine space is a two-dimensional plane. Instead of going from point A to point B, if you use enough gravity, you can wrap space around on itself and go from point A to point B instantly. Yeah. Sci-fi stuff.
Sci-fi?
That's all I could think
I'm really curious what science fiction is going to be like for your kids.